All right, let's dive into one of the most critical decisions in all of system design, storage. If you get this right, your application can scale to the moon. But if you get it wrong, well, things can get really messy really fast.
So this is the big question, right? It's the kind of thing that keeps engineers up at night. You're making this huge decision right at the start of a project. And if you mess it up, it is an absolute nightmare to fix down the road. So, how do we get it right?
Here's the secret. It's not about finding some magical, perfect database. That just doesn't exist. The real key is understanding that every single choice you make is a trade-off. So in this explainer, we're going to build a mental framework, a way of thinking, to help you navigate and totally master those trade-offs.
Okay, to build that framework, we first have to know what our tools are. So let's start with the 4 fundamental flavors of storage. Getting these down is really the first step to making any smart storage decision. First up, we've got block storage. The easiest way to think about this is like a raw external hard drive that you plug directly into a single server. It's incredibly fast, and its performance is measured in what's called IOPS. That's input-output operations per second. This raw speed makes it absolutely perfect for running the databases you know and love, like MySQL or PostgreSQL.
Next, there's file storage. Think of this like your classic shared network drive. It's super useful because multiple servers can all access the same files at the same time. This is great for things like shared configuration files or some older legacy apps. But it has one big weakness: network latency. Every single file operation has to go over the network, and that's just always going to be slower than talking to a local disk.
And that brings us to the modern workhorse for most unstructured data: object storage. We're talking about services like Amazon S3. Now, instead of a file system with folders, you just have this huge flat space where you store objects, things like images, videos, backups. Each one gets a globally unique ID, you can attach all sorts of metadata to it, and you get to it with a simple web request. And it's this architecture that makes it pretty much infinitely scalable. So you'll see this number thrown around a lot: 11 nines of durability. What does that actually mean in the real world? Well, it means that if you stored 10 million files in something like S3, you could expect to lose just one of them every 10,000 years. Yeah, it's a truly mind-boggling level of safety for your data.
And finally, for when you have a need for speed, there's in-memory storage. We're talking about tools like Redis or Memcached. Here, you're storing data directly in RAM, which is by far the fastest storage you can get. But don't just think of it as a simple cache. It's so much more. It's a powerful data structure server that can run things like real-time leaderboards, manage rate limits, and handle complex distributed locks, all at blazing speeds.
Okay, so now we've got our building blocks. Let's get to the real core of our framework. These are the 5 critical questions you absolutely have to answer before you write a single line of code to choose the right storage for your project.
Question number 1 is all about durability. When you say you want your data to be safe, what does that actually mean? Does safe mean it can survive a server rebooting? What about a hard drive completely failing? Or does it mean it needs to survive an entire data center getting wiped out by a meteor? Each level of safety comes with a different cost and complexity.
And this leads us to a classic durability trade-off. With synchronous replication, your app literally waits for the data to be safely copied to a backup before it tells the user, "Yep, got it." It's slower for them, but it's way safer. On the other hand, with asynchronous replication, the app tells the user "got it" right away and then copies the data in the background. It feels much faster for the user, but you're accepting a tiny risk of losing data if the main server fails before that background copy can finish.
Question 2, availability. And look, this isn't just some abstract number. This is a business question. How much money does your company lose for every single minute your system is down? How much trust do you lose with your users? The answer to that question tells you exactly how much you need to invest in keeping the lights on. And this table just perfectly illustrates what all those nines of availability actually feel like in the real world. Chasing more nines gets really expensive really fast. The difference between 3 nines, that's 99.9%, and 5 nines is the difference between almost 9 hours of downtime per year versus just a little over 5 minutes. That's a massive operational jump.
All right, next up is consistency. This is famously one of, if not the hardest problems in distributed systems. Put simply, it's about making sure that every single user, no matter where they are, sees the exact same correct version of the data at the same time. And trust me, that is way, way harder than it sounds.
This brings us right to the famous CAP theorem. It basically says that when your network has a problem, and it will, you're forced to make a choice.
Do you choose consistency? That's what a banking system does. It would rather go offline than risk processing a bad transaction. Or do you choose availability? Think of a shopping cart. It's better to risk a minor data conflict you can fix later than to stop a user from adding an item to their cart. You have to pick one.
Question 4 is latency. This is simply the measure of speed. How long does a request take to complete? And honestly, more than almost anything else, this is what makes your application feel fast or slow to a user. It is the silent killer of good user experience.
And your choice of storage has a colossal impact on latency. Look at this. Reading from a local disk is incredibly fast. Even network-attached block storage is still really fast. We're talking single-digit milliseconds. But the moment you jump to network file storage, that latency explodes by an order of magnitude. Why? Because of all the extra network round trips and protocol stuff for every single operation, those milliseconds add up incredibly fast.
And our final question is all about the future, scalability. This isn't about how your system works today. It's about how it's going to handle 10 times the users next year, or 100 times the users the year after that. Planning for that growth from day one is absolutely crucial, and there are 2 main ways to think about it. So you can scale up, which just means making your one server bigger and beefier. It's simple, but eventually you hit a wall, it gets super expensive, and you have a single point of failure. The other way is to scale out. That means adding more and more smaller servers to a pool. This gives you basically infinite potential to grow, but it also opens up a whole new world of complexity in managing a distributed system.
So, we've got our building blocks, and we've got our 5 critical questions. Let's pull this all together with a really common, real-world example that perfectly shows how to make a deliberate trade-off in action.
This is the cache aside pattern, and it's brilliant. When the app needs data, first, it checks the super fast in-memory cache. If the data isn't there, that's called a cache miss. It then goes and gets it from the slower but durable database. And here's the crucial part. It then saves that data back into the cache. So the next time it's needed, it'll be a super fast cache hit. This is a perfect trade-off. We are deliberately sacrificing strong consistency, the cache might be a tiny bit out of date, for a massive improvement in speed for most of our users.
And that really brings us right back to the central theme here. The most important thing to remember is this. Stop looking for the best storage. It doesn't exist. The sign of a great engineer isn't knowing the one perfect solution. It's understanding this entire landscape of trade-offs and making an informed, deliberate choice that fits the specific needs of their project.
So as you start your next project, don't just ask, what database should I use? Instead, ask yourself this, what am I willing to trade? Am I going to sacrifice a little bit of safety for incredible speed? Or will I accept a bit more latency to absolutely guarantee uptime? The choice is yours to make.